Welcome back. In today's lecture, I am going to talk about unconstrained optimization. Okay. So far, what we have seen, whenever we are solving some kind of optimization problem of some kind of functional, and functional we have defined like this, J, and after that I have T0 to Tf, L, X, X dot and T and dt. In this way we have defined, and after that what we found, that whenever some x star, that is some kind of function that is going to minimize this particular functional, then that is going to satisfy the Lagrangian equation. Okay, and obviously in order to solve the Lagrangian equation I need some kind of boundary condition, because that is second order differential equation when x belongs to R. If x belongs to Rn, so corresponding to each x I have second order nonlinear time varying differential equation. Okay, so everywhere, since whenever we are solving this class of problem, so x star is involved, and x star is nothing but some kind of function. So somehow we are dealing with some kind of optimization problem in infinite dimensional space. Okay, but if you see the development of calculus, then first we have started from the optimization problem of some kind of real valued function. Okay, so in place of this kind of functional, now I have some kind of real valued function. So f, and here x, and I am assuming that x has n number of component x1, x2, xn. So you can see that if some extremal point of f exists at that time, that will exist at some point x1 star, x2 star, or xn star. So somehow I am going to find the point or some kind of column vector such that that particular column vector is going to extremize this particular function. Okay, so since this column vector is going to lie in the finite dimensional space, so this class of problem is called finite dimensional optimization problem. Okay, but whatever problem we are dealing in the optimal control, so in optimal control I have to define some kind of performance measure, and after that I have to take care about the dynamics. Okay, and after that I can tell that I am going to design some kind of control such that whatever performance measure that is extremized. So somehow that is called dynamic optimization problem, because dynamics is also involved. Okay, in today's lecture I am not going to involve any kind of dynamics. So that is called a static optimization problem. So in a static optimization problem I have two possibility. That one possibility is that I have some kind of function and I have to minimize that function, or I have some kind of functional that I have to minimize. Okay, and we are assuming that there is no constraint. Okay, I will define the constraint, what is meaning of not constraint in the next part of this course. Okay, so I hope that you become familiar with these two classes of problem. So first I have proceed from the infinite and then I am moving to finite, such that now you are able to distinguish more closely. Okay, so let us start the today's lecture. So in order to solve any finite dimensional optimization problem, first I need some kind of function, and here you can see that this is real valued function. And why this function is real valued? Because I am assuming that whatever x here, this x is coming from some set of real number. Okay, it might possible x is some kind of column vectors, okay, and that column vector has n number of entry, okay. So one can now consider two different situations where x is nothing but that is coming from the whole space that I have Rn space. So I can tell that okay, x belongs to Rn, and then I have to solve or I have to minimize this problem, okay. So let us try to see. Suppose you have some function fx equal to x, and here for simplicity I am going to take x equal to r, real number, okay. So now could you please, anyone, could you please tell me that what is maximum value and what is minimum value? Anyone? Okay, Anchal, could you please comment that fx equal to x and x belongs to r? I am telling that x can take any value from minus infinity to plus infinity. And suppose if I have defined real valued function fx equal to x, okay, real valued means I have given some realistic data, and after that I am getting some kind of realistic data which belongs to the real numbers, okay. So now could you please guess that what is maxima and minima? Anchal,
Yes, sir.
could you please guess what is maxima and what is minima? Anchal, please answer the question. Could you please unmute yourself and then answer?
Yes, sir.
So what do you think? What is minima and what is maxima?
Sir, if it varies from minus infinity to plus infinity, then maximum value will lie on infinity, will be infinity.
Priyanka, what do you think? Priyanka Singh,
Yes, sir.
what do you think?
Sir,
Whatever answer
minimum
given by
value is minus infinity.
Anchal, that is okay. Shiv Prakash,
Yes, sir.
what do you think? Maxima and minima exist for this?
Actually, sir, no, not exist. Because it's taken a real number, then infinity is not a real number.
Yeah, actually, what happens that even if infinity is a real number, but I do not know what is that real number. Okay, and due to that reason, if you just consider x belongs to r, I cannot able to talk about maxima and minima, okay. And if you have just knowledge of school calculus, so most of time what students are doing, they are just first differentiating it,
Differentiate. Huh.
and if you differentiate it, you can see that x f dash x, then dx by dx equal to 1, okay. So now 1 is not equal to 0. So now a student become very confused. What is maxima and minima? Okay. So due to that reason, whatever condition we have learned so far, we have to see it carefully. Okay. Now what I am going to do, I am going to change my question. Okay. So what kind of restriction now I am going to put? I am going to keep restriction that is minus 1 to 1. What I am telling that now x is going to belongs from some open set minus 1 to 1. Okay. Now, Priyanka, could you please comment what is maxima and what is minima?
Sir, minimum value is minus 1.
Okay, and what is maximum?
1 plus 1.
Shikhar, whatever Priyanka is telling, that is correct. Shikhar Gupta. Shikhar, please unmute yourself and then answer.
Yes, sir.
Whatever Priyanka is telling, that is correct.
Yes, sir. If domain is minus 1 to 1, then maximum will be at 1 and minimum will be at minus 1.
Okay, someone could you please comment that why minima and maxima will not exist? Utkarsh.
Actually, it is open.
Okay, yeah,
Open
yeah.
set.
Binay.
It is open
Binay,
set.
please go ahead. It is open set. Okay. So
It is
open
open
set,
set.
it means that I don't know that what is minimum value of x. Okay. If I don't know, then how to put to calculate the minima and maxima. And due to that reason, again, if I have this kind of things, then I cannot able to talk about maxima and minima. Anyone has confusion? Now let us try to modify it further. If I will modify this like -1 and 1. Priyanka, could you please now comment that minima, what about situation of maxima and minima? Okay, Priyanka, are you able to understand why maxima and minima will not exist when x belongs to -1 to 1 open interval?
Sir, yes.
Now could you please comment if at 1 I have open bracket -1 and 1 I have closed bracket, then what is maxima and minima?
Sir, then maximum is defined at 1, but
Okay,
minimum
minima will
value
not
is not there.
define. So due to that reason, what I am telling, that whenever you have some kind of function, at that time you have to become very careful. Okay, so most of function, if you tell that x is free, there is no restriction, then it might possible this kind of situation basically comes into picture. Okay, so now question is that how to avoid this kind of situation. So could you please give some better suggestion? You can see here that whenever I am solving the maximization or extremization problem, at that time if I consider whole space, then most of time probability of existence of maximum or extremization, minimum or maximum, is violated, and due to that reason I have to restrict it. So if you restrict like this, then again I have problem. But if you restrict something like x belongs to -1 to 1, then I can tell, now I am able to comment that what is minima and what is maxima. Okay, so please check also for fx equal to x square and then give the comment. Okay, so due to that reason, whenever I am going to solve the finite dimensional optimization problem, so please be careful why I am telling finite dimension, because whatever argument x, that is basically going to lie in Rn, and but what I am going to do, if I will take any value from Rn, then it might possible I have restriction. Due to that reason, another suggestion is that you try to only consider some subset of the Rn. Okay, and due to that reason, whenever we are solving this class of problem, we are assuming that x belongs to D and D is subset of Rn. Okay, most of time whenever I have practical situation, at that time this kind of things are true. Okay, so another thing that I am going to consider very special space, that is called Euclidean vector space. What does it mean? I am going to assume that each entry of this column vector is coming from real number, and after that whatever inner product, or if we are going to see the distance between two quantity, then I am going to define using the inner product. Okay, because in order to define the distance between 2 points, I need norm. Okay, so just I am going to consider the Euclidean norm on Rn. What does it mean? That now I have a space, I have some kind of finite dimensional space where whatever vectors, column vector I am going to consider, that is coming from the real number, and after that in order to define the distance between two vectors, okay, whatever norm I am going to define, that norm I am going to define using inner product. Okay, so it may you are able to understand very easily. Suppose that in three-dimensional space, whenever we are defining the distance between these 2 points, at that time we are defining like x1 square, x2 square, x3 square. Okay, so what I mean to say that, and square root of this, so I am telling that d square is nothing but x transpose x. Okay, where x is x1 x2 and x3, like that. Okay, so whenever I am solving the problem, at that time basically we have to understand what kind of a space we are talking about, how to define norm, and what is beauty of finite dimensional optimization problem. In finite dimension, I can define norm in various way, but all norms are equivalent. Okay, so our result is not going to affect by selection of norm. So Binay, could you please now comment about what kind of difficulty that comes into picture if I will talk about infinite dimensional optimization problem in terms of the norm.
I think basis will be since infinite.
Yeah, basically actually what kind of difficulty we are going to face now whenever we are moving from finite to infinite. I have whatever I can define norm again in infinite many way, in infinite dimensional space also, but all norm are not equivalent. Okay, so optimization problem is basically very sensitive with respect to selection of norm. Okay, so if you take one norm, then it might possible whatever optimal result you are getting, that is different from if you go with L2 norm. So L1 norm, L2 norm, it might possible those who are working on control system, so they might have seen that we are defining control L1 control, L2 control, L infinity control. So but at least in finite dimensional space there is no need to worry about that. Okay, so up to here anyone has confusion? Now I am going to consider the real valued function. The argument of real valued function is going to lie in some subset, and subset is nothing but the subset of Rn. And after that I am going to talk about Euclidean vector space. It means that our our the our whenever I am going to consider the Euclidean vector space, at that time I have to define field. So field element is coming from the real number. Okay, because every vector space there exists some kind of field. So field I am going to take as a real number, and distance between two vectors or norm you can tell I am going to define using Euclidean norm, standard Euclidean norm, and I can able to take any kind of norm because all norm are equivalent. Okay, now let us come to the three different value of the maxima and minima. Okay, please give some time, something happens. Okay, so now what I am telling, that I am going to talk about the local, strict and global minima. Okay, so now whenever I am going to talk about the local, strict and global minima, so definition is actually just based on the our school same like a school textbook. Okay, but we have certain kind of restriction, means I am going to write everything very precisely. Okay, you can see here that what I am telling, that definition of local, and after that I will come to strict, and then I will land up to the global minimum. Okay, so what is definition of local? A point x star that belongs to D is a local minimum of f over D if there exists a epsilon such that for all x in D, if that satisfy that will lie in this ball, then I can tell that this kind of inequality will true. Okay, it means that if I will tell that x star is the local minima in some ball around x. Okay, so how basically we are creating ball? Suppose that if I have one dimensional space, then and this point is x star, then I am telling that in vicinity of this, basically this result will true. Suppose if you are in higher dimensional space, then if you construct some kind of ball, so ball ball is basically, construction of ball is totally depending on what kind of norm we are going to consider. Suppose that if you will take two norm, so at that time I am assuming that I have this kind of shape, some shape like this. So now this is x star and this is x. Okay, so what basically we are telling now, that for all x, if this relation will true, then x star is local minima. And what is radius of this ball? That is epsilon. Okay, anyone has confusion? So what basically we have to do, if some local minima exist for some real valued function, at that time I have to create some neighborhood, and I have to check that in neighborhood this kind of relation will satisfy or not. Okay, so here you can see that I am talking about less than equal to, but if you remove this equality, then that minima is called a strict minima. Okay, and what is meaning of global minima? That if I have some kind of minima, and that minima is valid everywhere in this region D. Okay, so if this relation not only holds in this particular ball but everywhere inside D, then that minima we are going to define as a global minima. Anyone has confusion? Now you can see that if we are telling that minimum is unique, at that time we are assuming that that is strict and global. Okay, otherwise that is, it might possible in our some subset I have more than one number of minima also. Okay, anyone has confusion? Or similarly, I can define the maxima, local, strict or global maxima, just you can reverse all the order, sign of order, fx star greater than equal to fx, like that. Okay, just you can reverse it. Okay, or fx, then you can just put minus sign everywhere in both side and then check the inequality, then same thing is true for the maxima. And due to that reason, whenever we are developing theory, at that time we are not considering about the maxima, because whatever theory that is exist for minima, if I just put negative sign, then same theory is also valid for maxima. Anyone has confusion so far? Then please let me know. So due to that reason, now you are able to understand that why basically we have selected Euclidean space, because somehow I have to make sure that if I take any 2 point in this particular ball, at that time this inequality should satisfy. Okay, so how to select that point? That is actually decided with the help of node. Okay, and due to that reason, I am not going to just consider vector space, but I have to consider vector space with some specific node. Okay, anyone has confusion? Okay,
Sir, could you please repeat strict local minima?
a strict local minima means just you can remove equality symbol. It means that I'm telling that fx star is less than fx, and for all x star, x minus x star less than equal to epsilon. Okay, so if this kind of condition that comes into picture, then I can tell that this x star is a local minima, a strict local minima. Any confusion?
Sir, what is D here?
D is the subset. What I am telling here, if you remember this discussion, okay, discussion here probably, yeah, I have started with some kind of function fx equal to x. Okay, or you can able to modify this function. One can also take this function 1 by x not equal to 0, and at x f x equal to 0, that is 0. Like that also you can define, or x square, whatever you can take. So if you are not going to restrict x, then it might possible I have some kind of unbounded function, and at that time I cannot able to talk about maxima and minima. Okay, and due to that reason, what basically we are doing, we are telling that now x, this argument is not going to lie in whole space, but that is going to lie in this subset of this space. So suppose you are dealing with two-dimensional space. Okay, so I have function like fx1, x2, something like that. Now I am telling that this function will actually, x will vary from here to here and x2 will vary from here to here. So by combination of this, I have this kind of a space that comes into picture, and now I am going to search minima, local minima, strict minima, global minima in this space only. Any confusion?
No, sir.
So D is just a subset. Okay. So if you don't have any confusion, then I will go to next slide. Now,
Then you just go to the previous slide, sir.
okay,
Sir, here. Sir, if the inequality, the third point, if x star is less than equal to fx,
yeah, is a strict. A strict means
is
equality is not valid.
okay. That means this is not true. If x star is less than fx,
No, what I am telling, if this inequality is a strict, meaning of a strict inequality is that f x star, I am going to remove this condition. That is the meaning. Okay, so mathematically one can write like this also. So I am telling that everywhere, if this inequality will true, x star less than equal to fx, then that is a strict local minima. Any confusion?
no, sir.
Nandita?
No, sir.
Okay. Now let us come to the next slide. So what I am telling now, the notion of local, strict and global maxima are defined in the similar way. And just now, if you are talking about minima of f, then in order to talk about maxima, just you can take -1. And due to that reason, most of time people are not developing separate theory for maxima and minima. Okay, because now we are mature guy, so there is no need to discuss two things at the same time. Okay, and one is obvious basically. So if a point is either maxima and minima, we are talking about extremum and extremization problem. Okay, now let us come to the definition, because when I have started this lecture, at that time I have told you that I am going to talk about the finite dimension. Okay, so I have justified what is meaning of finite dimension. I have also justified why I am going to talk about just a subset of Rn. I have also justified that why Euclidean space is required, because I need norm to talk about something, at least in order to construct the ball. And now we are going to justify another terminology, that is unconstrained. So the term unconstrained optimization usually refers to the situation where all point x sufficiently near to x star in Rn are in D. Okay, that is x star belongs to D together with Rn neighborhood. Okay, so what is meaning of this particular point? You might have seen whenever we are solving the extremization problem in infinite dimensional space, at that time we are constructing some kind of trajectory, and if this trajectory is maximal, then we are telling that variation of this with respect to this, that equal to arbitrary, so whatever coefficient, that should be 0. In that way we are telling, it means that in order to calculate the variation, I have to see the nearby of trajectory also. Okay, so if x star, this is optimal, then I have to check also what is x star plus delta x star. Similarly, x star minus delta x star. Okay, Similar kind of situation in finite dimensional space also. Suppose if I have some kind of function, okay, and if I am telling that this function has some specific property, suppose if you consider this kind of function, suppose for time being, and I am telling that at this point x star I have, suppose in this interval, this is the minimum. So I have to define the neighborhood also, okay, and I have to make sure that x star plus the increment of that and x star minus increment of that should lie on D. Okay, actually what kind of difficulty basically comes into picture, that whenever I have some kind of constraint, then at that time I have to always follow the constraint, and due to that reason I cannot give guarantee that if I am here, then after taking delta increment I remains here. Why? Because I have to follow the constraint also. Okay, and from here you can able to understand, suppose this is constrained surface like this, so I cannot able to move in this direction particularly. Okay, so unconstrained, whenever we are talking about unconstrained, it means that if x star point I am going to consider, then those kind of point which is sufficiently close to x star, that is again going to lie in the same space Rn, and that belongs to D, then only I can able to apply the proof or theory. Okay, that is the meaning. Anyone has confusion? But whenever we are going to consider the constraint optimization, at that time this assumption is not always true. Okay, we are going to see that in next lecture. Okay, simplest case D equal to Rn, which is sometime called the completely unconstrained case. Okay, it might possible I have some kind of function, okay, that will define in whole space, okay, and still I can able to talk about maxima and minima. Please try to find that kind of function by yourself, okay, because during a school time you might have seen several that kind of function. Okay, at that time it might possible I have maxima but not minima, I have minima but not maxima. Okay, so just for sake of example you can consider here this is R1, fx equal to x square. Okay, so is it possible to comment about minima for this function? Anyone, could you please comment? Yeah,
Minima is possible,
yeah,
maxima is not
maxima is
possible.
not possible. So even if my space is Rn, then it might possible I have minima but not maxima. Sometime I can construct some kind of example where I have both maxima and minima, okay, in whole space. Okay, due to that reason it might possible whatever problem, unconstrained problem I am going to solve, there is no constraint, and you are able to understand meaning of unconstrained whenever I am going to give the proof. So during proof you are able to easily able to understand that why unconstrained problem is so simple. Okay, and what kind of difficulty you are going to encounter whenever you are moving from unconstrained to constraint. Okay, so what I am telling now, however, as far as local minimization is concerned, it is enough to ensure that x star in the interior of the D. Okay, so what I am telling, suppose I have some kind of region. This region is D of some, and D actually subset of Rn, and if x star is here, then there is no need to worry. Either I can move here and in this direction, any direction if I will move, okay, then I can able to remains inside the D. It means that if I construct some kind of ball with help of norm, Euclidean norm, then that ball is going to lie inside that space only. But suppose if you are at boundary, then problem occur. Okay, so at that time I have to become careful. So in today's lecture we are going to see both the situation. If you are inside and if you are on the boundary, then what kind of modification is required in order to solve the unconstrained optimization problem. Okay, and D I am actually consider some kind of open subset of Rn. Okay, anyone has confusion so far? Okay, now first I am going to talk about first order necessary condition for optimality. Okay, so I have real valued function, and now in order to talk about the local minima, I have to also put some further assumption. And what kind of assumption basically comes into picture? I am assuming that whatever f that should be continuously differentiable. Okay, and you are able to understand why I am assuming this kind of restriction after some time. Okay, because this kind of assumption is required to prove something. Okay, and x star is local minima. So what I am telling, that pick a arbitrary vector d in Rn. Since we are unconstrained case, moving x star in the d or minus d cannot immediately take us outside. What I am telling, I have some space of d, and suppose x star is here. So if I select d in any direction, okay, so that will not going to leave this region. And due to that reason, what I am telling, that if I define x star plus alpha d, where x star is local minima that belongs to D for all alpha into R. Okay, alpha is some kind of real number. Okay, and D, this D point is basically belongs to Rn. So I have some kind of vector, x star is also vector, and here I am going to scale that vector. Since we are in vector space, and due to that reason this assumption is true, that I can able to perform a scalar multiplication and field element is real. Due to that reason alpha D, and after that adding this I am again remains in D. Okay, and alpha, how basically we are select alpha? Alpha is close enough to 0. Why I am telling? Because I know that x star is local minima. So x star is local minima, it means that if alpha is very close to 0, then this function x star plus alpha d will create x star. Anyone has confusion? And due to that reason, what I am telling, that I can vary alpha, and alpha is very close to 0. So here this is the situation for the alpha, either positive and negative, that doesn't matter. So let us come to the problem formulation. Now what I am telling, for a fixed d, we consider this kind of function of a real parameter alpha, whose domain is some interval containing 0. We have already seen that alpha I am going to consider, and domain means domain of alpha I have taken interval, means interval is the subset of real number. Okay, so I am going to consider some subset of real line, one dimension. Due to that reason this is real line, and after that what I am going to do, I am going to modify this function x star plus alpha d. Why? Because I have to make sure that if local maxima will exist at that time, this relation will always true. Okay, for all x star some norm in epsilon. Whenever I am in higher dimensional space, at that time we are defining norm like that, but you can define using one line also, then you can take that is norm in a higher dimensional space. Similar kind of things I have done. Now I can define a new function g, and this is function of alpha, because I know now x star is nothing but some kind of local minimum point. So x star is now fixed. Okay, now what I am going to do, this whole things I am going to vary alpha such that I am going to take care about the nearby of point. Okay, so x star is minimum of f. It is clear that 0 is minimum of 0 is the minimum of g. Anyone has confusion on this point? X star is the minimum of f, then I am telling that 0 is the minimum of g. Anyone has confusion on this point? What I am telling, that if you put alpha. So I know that this particular quantity fx equal to g0. It means that x star become equal to g0. So if this is minimum, so x star is minimum of f, and since these two functions are equal, so I can tell that okay, at the same time 0 is the minimum of g function g alpha, like this. Anyone has confusion? Okay, what I have basically done here, that initially I know that x star is the minimum, so I am going to shift it to 0. Okay, so without loss of generality, I can able to perform every analysis about the 0. Sorry. Now, whenever I am passing from function f to g, and g is a function of a scalar variable, what I am assuming now here, that this particular function, okay, so that is real valued function. So x star and d, that is lying in n dimensional, but g alpha, because here everything is depending on alpha, so this is just a scalar valued function. Okay, and whenever I have a scalar valued function, so I can apply the ordinary calculus, result from the ordinary calculus. And what I am going to do, I am going to perform the first order Taylor series expansion of g around alpha equal to 0, because now there is no difference between these thing, because I have defined g alpha equal to fx star alpha d. So if I put alpha equal to 0, then g0 equal to fx star. So if either I can solve problem for g or f, that doesn't matter. So if I solve problem for g, then for g, 0 is the minimum point. Okay, and if we are able to solve this problem, so automatically I can correlate our result with respect to f, and we are able to check that what kind of condition x star should satisfy in order to follow the same behavior like g alpha. Okay, and due to that reason, what I have done here, I have taken the Taylor series expansion. So if you see the Taylor series expansion, so alpha, so g0, since I am taking about the alpha, so basically what is basic motivation of Taylor series? Suppose if you have some kind of function, this is g function alpha, and if you have to perform Taylor series expansion here, so first you can assume that g alpha can be represented by some kind of constant. Suppose if that is not the true, then I will add some kind of c1, another constant, and after that I am telling okay, that can be represented by some kind of line, or I will move to higher dimension, similarly like c2, c3, alpha cube, like that. Okay, and after that, in order to decide the component, what you can do, you can put, since I am making I am doing approximation about 0, so you can put alpha equal to 0. So if you put alpha equal to 0, then all terms from here to here, that is 0, and due to that reason c0 is g0. So due to that reason I have written here. After that, in order to calculate c1, since you have just one equation, so somehow you have to remove c0. So I will take first derivative, and since I know the f is differentiable at least one time, so due to that reason g is also differentiable. So if you differentiate g with respect to alpha, then g dash c0 is 0, and c1 and all other term c2 to c2 alpha, and if you put alpha 0 again, then what happens, now c1 comes into picture, and due to that reason in place of c1 I have written like this. Similarly I can construct all term, and I am assuming that all higher order term using this, so this represent the higher order term of the O alpha. So there is no need to remember the Taylor series expansion, just you can remember this idea that any function can be represented with help of constant function, linear function, or some kind of parabolic function, ellipsoid function, or a higher order some kind of some function. Okay, and after that you can differentiate it, and after that you can calculate the coefficient. Now what I am assuming that in this particular Taylor series expansion, that whatever our this term, since alpha, I have to make sure that x star is our minimum point, and due to that reason I have to make sure that alpha is tending towards 0. Okay, so if alpha is approaching towards 0, I am assuming that this term is approaching towards 0. Okay, what does it mean? That all higher order term in this approximation, okay, since alpha is very small, and due to that reason higher order term become very small, than smaller than this particular term. So that kind of assumption I have. Okay, and this is true because I want to make sure that alpha is very small, then only I can tell that g0 is the minimum of this function g, or at the same time x star is the minimum of f. Okay, now what kind of claim I am doing now under this assumption, that g dash equal g dash 0 equal to 0. Okay, so how to prove this? First you can assume that g dash not equal to 0. So what I am going to do now, I am going to give proof by contradiction. So I have to prove this. I am assuming that this is not true, because in mathematics only two situations, either things are true or false. Okay, so something if you have to prove that true, so what you can assume that false situation, and after that you can tell that that false things is not possible, then automatically that quantity is true. So same way I am going to proceed. Okay, now what I am telling that since alpha tending towards 0, at that time I am assuming that higher order term is decreasing very fastly than this. It means that for every epsilon that is small enough so that if alpha is less than epsilon, then this particular quantity, okay, that is less than g dash 0. Okay, so mathematically I can also write like this, that if I can select alpha very small, it means that if x star is here, so I have constructed some kind of ball, and here I have taken some vector d and alpha, and I am varying alpha such that I have created this neighborhood. Now I am telling that if alpha, one dimensional alpha, that is actually lie in this region, okay, at that time all higher order term that is lesser than this. Okay, and it is possible to show, it is not difficult to show that since we are taking the Taylor series expansion, and if alpha is very small, then this term is practically very small. And now using this kind of result, I can able to make some kind of correlation between g dash 0. Okay, so what does it mean? That rate of change of the function, first order rate of change of function dominate over all higher rate with multiplication of alpha. Okay, so if you substitute in place of O alpha this kind of inequality, then it is possible to show, and I am going to recollect it, g alpha minus g0, then I can show that g dash 0 alpha plus g dash 0 and here alpha. Okay, and here alpha might be negative and positive. Okay, so you can take those kind of situation where g dash alpha and alpha both are of opposite sign. Okay, so if both are of the opposite sign, because alpha, any variation of alpha is allowed, and due to that reason I can assume that that is positive or negative. Due to that reason this quantity is negative. Okay, opposite sign, so one is plus, then another is minus and plus. Okay, so every combination this result should true. Okay, so what I have taken those kind of situation which is called worst situation. So at that time you can see that this will compensate this. So under that situation I can able to show that g alpha is less than g0. Okay, what does it mean? If alpha is small, then I have some function g that is greater than g. Okay, so that is contradict the definition of minima, because I know I have to prove that g0 is minima, so I have to prove this. But what happens by definition? But what happens? I come up with this kind of inequality, and due to that reason, if I assume that g dash not equal to 0, then some contradiction kind of condition comes into picture, at least in some specific case, and due to that reason I cannot assume this. Okay, so I have only one conclusion, that g dash equal to 0. So in this way you are able to prove that why g dash equal to 0. Okay, so similar kind of things I have actually written here. Now once I understood that g dash 0 equal to 0, then now I know that this function and this function x star alpha d both are correlated. So I have to formulate our expression in terms of the original function, because I am going to minimize original function. So I have minimized this function, and after that now I am going to correlate with the original function. Okay, so my original function is basically f. So what I am going to do, I have to calculate g dash equal to 0 because I have just proved it that if this condition will true, then I have always minima. Okay, so what I am going to do now, I am going to apply first order derivative on both sides, and since f, if you see now, then f is multi-valued function. Okay, x star or x that belongs to D, and D is subset of Rn, and due to that reason I have to calculate the gradient, and after that D is vector. Okay, and since left hand side is a scalar, so I have to make sure that this is also a scalar quantity. Okay, so if I assume this as a, you can see here that I have assumed this as a column vector, then what happens, I have to make sure that D is as a row vector. Okay, and then only that will produce some kind of a scalar. Anyone has confusion, then please let me know. And sometime for the convenience, people are also writing like this. This is the representation of partial derivative. So it is possible to show that g dash 0 equal to this gradient of f at x star and d, because I have to make sure that if alpha is very small, practically 0, then whatever condition for the existence of the minima, same kind of condition I am going to substitute here, and due to that reason I have substituted alpha equal to 0. So if you substitute alpha equal to 0, then I have this kind of situation, and I know from the proof just now that g dash 0 should be 0. Otherwise one cannot tell that function g has a minima, and due to that reason if you put g dash equal to 0 and d is arbitrary, due to that reason only one condition, that gradient of f about x star should be 0. So this is called first order necessary condition for optimality. Okay, so if this condition is satisfied, then only I can tell that x star is the minimum. Okay, similar kind of situation I can derive, similar kind of result I will derive for maxima also, just putting minus sign. And due to that reason we are telling that first order necessary condition for optimality, not for minimum and maximum, because both condition will generate the same function, same result, that gradient x star equal to 0. Anyone has confusion till now, then please let me know. Okay, if you don't have any confusion, then now what I am going to do now, I am going to give some name to x star, because x star now may be maxima or minima. Okay, why maxima and minima? Because if I will consider function f, then you can generate result with minus f. You are going to learn to the same thing, and due to that reason now I cannot able to understand that this is maxima or minima, and due to that reason this is called a stationary point. Okay, So how to calculate a stationary point? Just you can take the gradient and keep gradient equal to 0. So that will give you the stationary point. And why this is called first order? You can see here that I have written first order necessary condition. What is meaning of first order here? Because I am assuming that in this Taylor series expansion, this first order term is dominate over all higher order term, and due to that reason this is called first order expansion. And please be careful that we are assuming that function f at least one time differentiable and x star is the integer of the D. Okay, now another necessary condition one can derive, and at that time I have to actually increase the restriction on the function. Okay, and what I am going to assume now that function f is two time continuously differentiable. It means that two is continuously differentiable. Okay, so if I assume this, then again I am going to derive the another necessary condition. Okay, so could you please guess that if I consider that function is two time continuously differentiable, then what kind of assumption I have comes into picture? Could you please guess? So what I am going to do now, I am again going to expand that function fx. Okay, and since I am telling that x star is minimum, so I have to again convert x star into g, and I am going to take now Taylor series expansion up to second order. Okay, and then I am going to put the condition of necessary condition of the first order, and then I am going to check that under that situation what kind of extra condition that comes into picture such that minimum occur. Okay, so what I think that I will discuss this point in the next class, otherwise class become very of long duration. Okay, so 50% part is still remaining. So what I will do, I will I will discuss the second order necessary condition in the next class, and after that we are trying to understand that how to use the concept of local minima to find the global minimum of some function. Okay, and I am going to assume that if that function is two time differentiable. Okay, then how to find necessary and sufficient condition such that I can give guarantee that some function has some kind of local, strict or global minima. Okay, so now it is time to conclude the today's lecture. So what is main theme of today's discussion? That we have identified the difference between the finite dimensional optimization problem and infinite dimensional optimization problem. Okay, and what basically we have concluded that infinite dimensional problem, basically whatever norm I am taking, so what is beauty that all norms are equivalent, but I cannot assume same kind of things for infinite dimensional case, and due to that reason I have to take extra care. Okay, so first I have proceed with the finite dimensional optimization problem. We have identified the space. Okay, we have identified the norm. After that, what we have done, we have seen the assumption that when under which condition I can able to solve this problem, and after that we find out some kind of condition in terms of gradient such that we have a stationary point. Okay, and in next class I am going to extend same kind of idea whatever we have learned so far to give some kind of necessary and sufficient condition for the existence of the optimality. Okay, with help of the same discussion. If anyone has confusion, then please let me know. because most of time what happens, why I have actually started again with the finite dimensional, because most of time students are not precisely familiar with the finite dimensional optimization problem. They don't know why we have to select a space, what kind of restriction we have to assume. You can see that when I have started this lecture, I have started with fx. Okay, and when I will ask question to a student, then they are telling that minus infinity and plus infinity is maxima and minima. And due to that reason, we have to become very careful before going from finite dimensional to infinite dimension. Okay, because now school time is over, we have to become more precise. Okay, so in how to become more precise, we have to understand where, in which space basically we have formulated the problem. Okay, what kind of restriction that comes into picture such that problem is solvable, under what condition problem is not solvable. So we have to identify each and everything. Okay, so with this remark I am going to in the today's lecture. If you have any confusion, then please let me know.